So what we're going to explore in this video is inverse functions. So what we're going to start with, okay, we're going to do a little investigation together. We're going to let f of x be this function 2x plus 3, and we're going to let g of x be the function x minus 3 over 2. And so the first thing is we're going to make a table of values for each of these. And now I'm going to specifically give you values I want you to plug in. Okay, so for function f of x, I want you to plug in -2, -1, 0, and 1. Okay. And let's do that now. So we're going to plug in -2. 2 times -2 is -4 plus 3. That gives us an output of -1. Plug in -1. 2 times -1 is -2 plus 3. Gives us an output of +1. Plug in 0. We get 3. Plug in 1. We get 5. So now, what I want us to do is, I want us to take the outputs of f of x and make them the inputs of a table for g of x, okay? So -1, then 1, then 3, then 5. Okay, so now let's plug -1 in. -1 minus 3 over 2, that's going to be -4 over 2, that's going to be -2. Okay, plug in 1. 1 minus 3 over 2, that's going to be -2 over 2, that's going to be -1. Plug in 3, that's going to be 3 minus 3 over 2, that's going to be 0 over 2, that's going to be 0. Plug in 5, 5 minus 3 over 2, that's 2 over 2, that's 1. Okay, very interesting. Look what happened. Okay, this must have something to do with our topic here, inverse functions. Now, what we're going to do is we're going to graph this, okay? Now, it's not going to look perfect because we don't have graph paper here, okay? But we're going to try our best. So I want to graph both of them on the same plane. I'm trying my best here. Make this as perfect as I can. Okay, so -2, -1, -1, 1, 0, 3, and 1, 5. Okay? So that's f of x. G of x will be -1, -2, 1, -1, 3, 0, and 5, 1. Now, it might be hard to tell because of the fact that we are doing it just freehand here, but there is actually a line of symmetry. Okay, and let's label this. This is g of x, and the line of symmetry is actually the line y equals x. This is actually serving as the line of symmetry between f of x and g of x. And think about this. Think about what this statement is saying. The linear equation is y equals x. So if you had graph paper and you did this, you would definitely see that this is a line of symmetry. So if you have graph paper, I would suggest you try graphing both of these on the same plane and seeing that this is actually happening. Well, look what this equation says. The y equals x. It says whatever y is, that's what x is. Whatever x is, y is. Look at what we have here in our table. Okay, that's really y. That's really y. Whatever x is here, that's what y is here. Whatever y is here, that's what x is here. That's why we're seeing that symmetry over the line y equals x. Now, I want to show you something else that's pretty interesting here. If we wrote out in words, what is f of x? What's happening to x in f of x? We would say x is being multiplied by 2, and then, or we could say, and the product is being added by 3. And in g of x, x is being subtracted by 3. Okay, and then the difference is being divided by 2. Do you notice anything between these two? F of x is saying take x, multiply it by 2, and then add 3. In g of x, it's saying take x, take away 3, and then divide by 2. Okay? You're doing all of the opposite operations and in the opposite order. They're actually called doing the inverse operations. Multiplication and division are inverse operations. Adding and subtracting are inverse operations. Okay? So basically, these two functions are undoing each other. So think about what you would be left with if you undid all the other operations. Okay? Think about what you would be left with, because we're about to look at that right now. Okay? So we've looked at all of this. Look at these tables again. Take note of what the line of symmetry is. Think about this information. And the next thing I'm going to have us do is do some function composition. Okay? Let's do f of g of x and g of f of x. Okay? So this says I'm going to take f and I'm going to stick in g. Now notice, g of x is really saying, okay, my input into g is x. My input into g is x. So I wonder what my output of f will be. Okay? So I'm going to stick g into f. So that's going to be 2 times x minus 3 over 2 plus 3. 2, that's the same as 2 over 1 times x minus 3 over 2, right? Those cancel. This would leave us with x minus 3. Bring that down, right? Plus 3. That leaves me with x. So f of g of x simplifies to be the function f. So what this statement is literally saying is the input of g is x, and the output of f, or f of g of x, right, of f, is x. Okay? And let's see if it happens again. Okay? So we're sticking f into g. So that means we have 2x plus 3 minus 3 over 2. Nothing to distribute out here, so it's just 2x plus 3 minus 3 over 2. 3 minus 3, they cancel. That leaves you with 2x over 2. That leaves you with x. It happens again. We just got g of f of x equals x. These are huge statements. What this is saying is, whatever you input into g, you're outputting out of f. Whatever you input into f, you are outputting out of g. The same value. Whatever you plug in, you're getting. Whatever you input to f, you're outputting of g. Okay? So these two statements are super important. This, okay, all of this. Now I'm going to tell you one big thing. F of x and g of x are what's called inverses. They are inverses of one another. These two functions right here are what is considered inverse functions of one another. So everything that's true about inverses is everything we just went over. So to recap, okay, if two functions are inverses, this is what you must be true, okay? The following. We'll call them f of x and g of x. Those don't have to be their names though. First thing that has to be true. The input of one is the output of the other. and the output of one is the input of the other. So if you have function f of x and you have function g of x, whatever is the domain of f of x becomes the range of g of x, and whatever is the range of f of x becomes the domain of g of x. So that's number one. Number two, when you graph them both, the line of symmetry, when you graph f of x, when graphing f of x and g of x, is the line y equals x. Okay, so if you looked at it graphically, if they were not reflections over the line y equals x, then they would not be inverses. You could also look at it through, okay, the domain and ranges. If their domain and ranges were not flipped, then, okay, wouldn't work. Number three. So number three is, okay, this is how, I'm going to write this because this is important. This is how you verify inverses. Okay, this is how you prove that two functions are actually inverses of another. Because you can't just prove from a table, you can't prove from a table of values that you are inverses, because a table of values does not have an infinite set of the ordered points that make up the function, because if you are an inverse, if two functions are inverses, every single input and output have to be swapped, okay? Not just four of them, okay? So to verify inverses, you need the general. How do you check every single coordinate point that would make up both functions? Well, when you do f of g of x, so when you do the composite, when you stick g into f, you better output back out x, because what this is saying is whatever you input into g, you're going to output into f, which is what the definition of inverses is, right? The input of one is the output of the other. So both of these have to be true. When you take the function composition of f of g of x, you need to output x. And when you do g of f of x, you need to output x. But it's really important to understand these two statements. This is saying, whatever you decide to plug into g, you're going to get out of f. That is true, what it means to be inverses. Okay? The input and the output have swapped. So what we're going to do in future videos, okay, we're going to go over how to algebraically find the inverse and making sure we can verify that two functions are inverses of one another.